Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. Thank you very much, Chris. I'm Jeremy Gibbons from the University of Oxford, and I'm going to talk here about we had a very nice introduction to health issues in impoverished rural communities, mountainous communities as well, in this case highland communities. And I'm going to talk about briefly about a study that we're involved with there in Kathmandu. So this different continent, but very much a similar environment, and how the semantic technologies that we're developing at Oxford are contributing towards this study. So the particular concern here is pneumonia. This is the top-ranked disease in the previous talk's list of health concerns. And it's a huge problem. This is a graph from a diagram from the World Health Organization, which shows deaths from pneumococcal disease. Each one of these red dots is 1,000 deaths. You can see they're clustered across the middle of the globe, so they're clustered in the poorer areas. This represents 1.6 million deaths annually. Half of those deaths are in young children under 5 years old, and 90% of those young children dying of pneumococcal disease are in developing countries. So it's a very big issue in healthcare in the developing countries. It's the number one preventable cause of death in young children, preventable through vaccines. So my colleague Jim Davies and I are working with the vaccine group in Oxford, and obviously they're very interested in this area. It's where they get the greatest leverage for their efforts in terms of public good they can do. So one of the problems with pneumonia and related diseases is that there's even in the developing world there's a growing resistance to antibiotics. So treatment is getting harder and harder, and so prevention is becoming much more important. So immunization is where it's at. This is what people are trying to do. I'm going to tread on somewhat thin ice here. I know very little about the domain, about pneumococcal disease, but I understand that there are 91 different variants of pneumococcus, the serotypes they're called. So there isn't just one disease. There's many mutations of this, and the mutations that you find in a community differ from community to community. So the profile of pneumococcal disease varies, and it varies over geography, and it varies over time. So what you find in the West is different from what you find in Africa. And what you find in Africa now is different from what you found in Africa 10 years ago. So out of those 91 different varieties, different serotypes, the 13 most common ones cause a large proportion of the disease in children. So this is usually the case. There's a sort of 80-20 rule going on here. The most common small proportion cause a large proportion of the problem. So over the years, people have been working on vaccines. In the UK, there's so the current vaccine that's most commonly applied is particularly aimed at elderly people. And it covers 23 serotypes, so it's called a 23-valent vaccine. And that's been trialled and shown to be effective on elderly people in the UK. But that drug doesn't work well on children. It doesn't have a strong effect on children. So although this has been tried on elderly people, this is not something that is going to work well dealing with childhood disease. There is a new vaccine called PCV7, polyvalent, I can't remember what it stands for, polyvalent conjugate vaccine covering 7 serotypes, so covering 7 common variants of pneumococcus aimed at children, but it's been aimed at, developed for children in the West. So it deals with 7 common serotypes that crop up in the spectrum that you would find in the West, but because that's different from what's happening in developing countries, this vaccine is not much use in Africa and Asia either. Current drug development, vaccine development, is looking at 2 other vaccines there, PCV10, which has recently been licensed, and PCV13, which is currently awaiting approval. So these are different collections of these address different collections of serotypes, and they're particularly aimed for the profile that you find, the spectrum that you find in developing countries. So the study that we're involved with is with our vaccinology colleagues, Andrew Pollard, Matthew Snape, and Jane Metz, and others mentioned in the paper, looking at the PCV10 virus in particular, and trying it out on infants, so young children, very young children in Nepal, and looking to see how effective it is. So we're carrying out this study of pneumococcal disease vaccines. So to relate this to my interest now, to the computer sciencey aspects, the software engineering aspects of this, this is a study, and we've been developing software tools to support the conduct of these studies, execution of studies, trying to deal simultaneously with 2 problems, 2 aspects of these studies. One aspect is trying to improve the science, and the other aspect is trying to reduce the cost of developing these software tools. So the science-wise, we've most trials tend not to give you very strong results. They don't give you enough diagnostic power because it's difficult to recruit enough participants. So the current best practice in medical research is to try to collate the results from multiple trials, to do meta-analysis, it's called. So rather than just looking at the result of one trial, trying to integrate multiple data sets that have risen out of multiple trials. And for this to work, it's vitally important to have more than just the numbers that were collected in a particular experiment. In this case, the various readings that are taken from when you're conducting a trial. It's vitally important to have the semantic metadata associated with those numbers, so that sometime later, when the original investigators have gone, they're no longer interested, they've retired, this data is still useful because it's still properly described, and you, in a sense, you know what the column headings on the tables are. It's not just a list of numbers. It's not even just a list of numbers that says this is a blood pressure. The columns in the table have relatively rich semantic metadata that says the units, the procedures, the process by which this blood pressure was taken, everything else you need to know in order to decide whether this column of numbers collected in one trial can be integrated with a column of numbers conducted in another trial. So semantic metadata is vitally important in putting together the results of multiple trials. And the other aspect of the story is trying to decrease the drudgery involved in developing software support for trials, for studies, for scientific experiments. The current practice here is the scientist, the clinician, the vaccinologist, or whatever will sit and think with their scientific hat on. They will determine an experiment that they want to conduct, this PCV10 trial in Nepal in our case. They'll write a document that describes what they want to do. They'll use that to apply for funding to conduct the trial. They'll use that to apply for ethical approval because it's a trial on human participants, presumably. And they'll hand this document over, assuming it gets funding and assuming it gets ethical approval, the trial is ready to go ahead. They then need some kind of information system support to conduct the trial. There are going to be forms that need to be completed. Data would need to be collected from those forms and entered into a database, and then statistical analysis conducted on that data. So current practice is to take the textual document that was used, the trial protocol, and then hand that over to database developers or software developers to go and design the forms, produce the perhaps web services that let people, let the nurses conducting the trial enter the data that they're collecting. They design the data layouts, a relational database to keep the results in. And of course, from one trial to another, these things are all slightly different. The shape, the content of the form, the data that you're going to collect, the column headings in the database or in the spreadsheet, they're all going to vary from trial to trial, but they're all very similar. They're all sort of instances of a common general scheme. You can think of this as a software product line for clinical trials. And in each case, you produce an instance of this product line. And it's extremely inefficient to produce each of these instances of a software product line manually from scratch every time. So with model-driven development tools, model-driven generation tools, we can produce software that is customized for a particular trial. So the forms that you produce have fields for exactly the data you need for the trial, the services, for example, for accepting the data that you're collecting and validating the data, know what the valid range of values to put in a field is, and so they can reject invalid forms or incomplete forms. The database schema is custom to a particular trial. This can all be done producing a software suite that is exactly customized for a particular trial, but without having all the costs of handcrafted development. It's a sort of customized behavior with off-the-shelf costs. So the approach that we've been working on combines these two aspects, semantic metadata for properly marking up the meaning of the data you're collecting, and model-driven techniques for generating the software tools. Putting the two together, is synergistic, if you apologize for the word, but in the sense that it's often the case that you evolve the design of the study maybe as the study progresses. If it's an early phase study, you don't quite know what you're looking for, so you'll try something, collect a few bits of data, and then refine your questions, add an extra field, and so on. So the semantic information that you want to collect and propagate with the data can vary over time, and it's then extremely important that it's a low-cost exercise to regenerate the forms and the services and the database formats and so on for conducting the trial in this new version. So not only are these two aspects important, the second aspect is very important for supporting the first. They're very important together as well. So we've been calling this work CancerGrid for what seemed like perfectly good reasons at the time, although it's not anything that's specific to cancer and it's not really anything grid related, so we're inclined to be a bit apologetic about the name these days. This was a 5-year project from 2005 to 2008, funded by the UK Medical Research Council. But we have a collection of follow-on funding, some of which from Microsoft Research that we talked about at this workshop last year, but also Engineering and Physical Sciences Research Council in the UK and European Union funding. So there's various follow-on bits of work. We're putting it under the heading of CancerGrid. It's the same technologies. So we've taken this general approach and identified some tools that you need to make it work. And the tools that so the essence of the approach is tools for supporting a research community in identifying, classifying, curating, versioning, generally maintaining a collection of metadata, the semantic information with which you will mark up a study. And so this will include the types and descriptions of the fields that you want to collect, the procedures you're going to use to collect them, and so on. And that then that's part of the metadata aspect, and then the model-driven aspect, the software product line. You need to somehow characterize the entirety of the product line, the whole product line, the family of products, from which you're going to draw instances. And in this case, so this is a metamodel of the experiment you're going to conduct, so of the clinical study you're going to carry out. Metamodel because the trial protocol, the textual document that you used to write, is a model of the study. It's a rather informal model. It's a model written in Word or in text, in prose. Our generation techniques use a structured model rather than an unstructured one, so it's basically an XML document, but it's still a model of the trial, and the description of the software product line is a model of trial models, so we use the term metamodel for that. And then model-driven techniques that take a model of a study, the description of a particular study, and translate that into software artifacts for conducting the study, so blank forms, services for accepting forms and for validating them, database, so XML databases or custom databases or what have you. And the forms that collect the data, the services that accept the data, the databases that maintain the data are all annotated so that any semantic information is clearly labeled on the form. There's you can put the process by which you're supposed to collect some data in a comment on the form, so that the nurse knows what to do, what protocol she should use for collecting, for reading blood pressure, for example. But this data can be copied and propagated. The metadata can be copied and propagated with the data, and so is always associated with the data throughout the life of the data. So our initial studies on this were with breast cancer clinical trials. We've been looking at ovarian cancer clinical trials, but we reckon this is nothing specifically to do with cancer. So we've been looking at these vaccinology studies as well, and that's what this talk is about. The metamodel I'm going to show you briefly is, so this is a metamodel of well-designed trials. And this is not something that we've come up with ourselves as software engineers in the CancerGrid project. We don't know, we're not authoritative in what makes a well-designed trial, but fortunately the clinical research community has done that for us. They have already got together and come up with what's called the Consolidating Standard of Reporting Trials, which describes all the data that you should collect. Best practice in designing the data that should be collected in a trial. This is called the CONSORT statement. This is basically it's a textual checklist of what should be recorded in a trial. We've taken this and made it a structured metamodel of well-designed trials, CONSORT conforming trials. And this is the basis for our model-driven generation tools. They work on a metamodel of the domain, and in the domain of clinical trials, this CONSORT-based metamodel is our metamodel. Here's a fragment of it. This is a UML class diagram, but there's just kind of some entity relationship mechanism. This shows, it's probably illegible, I'm afraid, but there's a reference in the paper to where you can find the technical report describing this. On the left-hand side, it shows case report forms, and case report forms consist of sections, and sections have elements in CDEs or rows, that says, so common data elements or rows. And the form itself and the sections of the form have authorization attributes, so that the form or bits of the form might need to be signed. Down the right-hand side, there's some of the structure of common data elements, references to common data elements, and common data elements with skip logic, so common data elements that are optional. Depending on the value you fill in one field, the subsequent field might be disabled. So there's a UML model in our case of the domain. In this is a fragment of the UML model of CONSORT compliant trials. So the kind of stuff that you would record in describing a study are the specifics of this trial. The metamodel characterizes trials in general, and then when you're building a model, you say, well, what's different about my trial? What's special about my trial as opposed to what's in the domain? And so you're going to describe the data elements that you're going to collect, the types of information, valid ranges of age and height and so on, perhaps. You might be considering eligibility criteria, so that you might only want non-smoking women between 20 and 70. So there are Boolean properties that can be determined from data that's recorded that will tell you whether or not a particular participant is eligible for this trial. You might record stratification variables, so if it's the trial might compare one treatment with another treatment, or people in a given age range against people in another age range. So you might want to divide your population up into subpopulations based on their age, based on the treatment you're going to give them, based on any number of other properties. So these are called stratification variables. You're going to describe that when you describe your study. And then your study also contains descriptions of some of the software artifacts that you're going to collect. The form design, for example. These should also be described as part of the model, because this information is going to be used in generating the software artifacts. So we have model authoring tools that instantiate the metamodel to produce a model of a particular trial using standard information out of a metadata registry. So your community, however wide that is, hopefully is spent some time considering what are the sensible things to collect and what are the sensible formats in which to collect them, and recorded this in the metadata registry. So we think age is a good thing to record. We don't want you just to classify people as young and old. We want you to actually record their date of birth. If you only want whether they're in their 20s or whether in their 30s, you can represent that as a derived variable from their actual age. The actual age is much more useful when it comes to interoperability, when it comes to meta-analysis. Your division of age into 20s and 30s and so on might be convenient for you, but it might mean your data doesn't match another data set where the buckets are different. So the community gets together and decides the appropriate variables to be captured. So our tools are designed to help you collect this data, collate it, catalog it, and maybe version it as well. So you might want to have sort of local customization, although the sort of national practice for how to do this is to do it one way. In this community, in this institute, in this group, we're going to do it different. We realize that's different from the standard, but we have good reasons for doing that. It's unrealistic to expect everyone to conform universally to the same standard. So this is briefly the workflow of producing a software system to support a trial and then conducting the trial. At the top left, there's the metamodel is expressed as an XML schema. And then at the top right, the scientist designs, models the trial and produces an XML document to describe that. In our case, we do this using Microsoft InfoPath, that you load in the schema that classifies well-designed trials, and InfoPath will say, looks like you're trying to build a trial here, would you want some help with that? And you can drag and drop fields in the trial designer and produce a model of a particular trial, which in some sense, down at the bottom left, is an instance of the trial metamodel. And then the nurse takes this trial metamodel, so this trial model, and says, well, I'm going to register a patient, so I need to get a form for the patient, I need to type in their name and their age and whatever other information. This is done, again, can be done with InfoPath. So the trial model is a schema for the data to be collected on one patient, and again, you can load this into InfoPath. InfoPath says, looks like you're trying to record information on a patient here, would you like some help with that? And you drag and drop, fill in the form, and you get another XML document, in this case, that describes a particular patient, a case report form, the content of a case report form. So the CancerGrid approach, in essence, is domain modeling, but in this case, because the domain consists itself of models, when you model in the domain, it's meta-modeling. You instantiate the meta-model to produce a model of your particular experiment, your trial, your study, whatever it is. You annotate your trial model with the semantics of the thing that you're trying to record, the data you're going to collect. You generate from your trial model some software artifacts, some forms, some services, databases, whatever. And these software artifacts are, by construction, they will collect and propagate the semantic metadata. And we do this by we haven't been hand constructing software tools ourselves. We've been taking the software product line view ourselves and saying, well, standard office productivity software like InfoPath and Excel and so on are actually very well designed for doing this, and they're very familiar to our target audience, and they're customizable through plugins. So we make this approach available through plugins to standard software. The end result is a service-oriented architecture for conducting the trial, in the sense that the forms are electronic forms, they're submitted via web services, the data is stored in a database, and these can all take place in different locations. The data can be collected by a nurse in a clinic. She fills in a form and submits it to a trials unit that might be somewhere else. The trials unit stores its data. That might be in a third place altogether. I'll skip over that because my time's running short, but just to say, closing the circle, what this has to do with vaccine studies. The model-driven approach we've taken is extremely appropriate for low-budget contexts. So the Oxford Vaccine Group up the road from us is not a particularly low-budget setup, but they have financial constraints, and in particular they're developing very small exploratory studies, and they can't afford to spend months of a developer time developing tools to support a tiny little study. We can automatically generate the software to support a particular study. And of course, if you're trying to set up a study in a developing country, you can't afford to spend large amounts of money on big corporate information systems or handcrafted development, so model-driven approaches are very helpful there. The service-oriented architecture turns out to be very helpful, again, in low-budget contexts. So, the study is being conducted in Nepal. The data collection is done in Nepal. The infrastructure there is poor. The postal service is not reliable. The internet connections are actually much better, whether those are by wireless or perhaps by mobile phone connections, PDAs, and so on. So this approach turns out to be very good for rural communities. We like it because it's another exemplar. It's evidence that the CancerGrid approach is not specific to cancer. Other kinds of disease with standard collections of data are also good matches. And we also like it because the big cancer trials that we've been looking at have turnarounds of years, so it's rather slow for us to validate our approaches on that. These vaccine studies are quicker and smaller, and so we get faster turnaround, so that helps. And the PCV10 study that I started with, that's currently undergoing ethical review. It's got financial support from indirectly from something called Gavi, the Global Alliance for Vaccines and Immunology, which is itself supported by the Gates Foundation, partially supported by the Gates Foundation. So this trial is due to start soon, and we're generating the software tools for conducting it. And I'm going to stop there. So thank you very much.
Questions? Just a quick one. So the Gates Foundation supporting the Kathmandu trial?
Indirectly, I mean, through several levels of indirection. So the Gates Foundation partially supports this Global Alliance for Vaccinology and Immunization, what it's called. And they support the HIB initiative at Johns Hopkins, which is funding the trial. We have, yes. We mentioned this, but that's another topic, I think. Yeah.
Yeah, we actually did take them down there a few weeks back.
Yes, so Jim and our oncologist colleague James Brenton went to visit.
So you kind of took the question right out of my mouth that I had for you, which was you talked earlier about it reduces the drudgery, but really it's this fast turnaround, right? In particular when we're talking about phase 1 and phase 2 type clinical trials. But wasn't the system originally targeted? It was actually for phase 3?
Right, so the initial exemplars that we did with CancerGrid were phase 3 sort of trials, and they're different. I mean, they're much more standardized. They have a very firm question that you're trying to answer, and you don't evolve the study as you go along. And it works nicely for that. The approach works very nicely for that. But it works better I mean, it's even more difficult to use handcrafted approaches where you're working on small studies where they keep changing, where you don't know quite what the question is until you're halfway through it. And so it's, these earlier phase studies are even more attractive subject matter.
Yeah, but just in particular because most studies are conducted on paper.
Well, indeed. I could have, when I give this talk, variants of this talk, I often start off with a photo of the problem, which is a desk with, I mean, the trial protocol, which is a 100-page document, and then a big stack of case report forms. And the data gathering is pen and paper exercise, filling in the forms, and these then get posted back to base and typed into a database, which is a waste of effort and introduces errors.
Right. Doing it in silico then just
Yeah.
makes, in particular for these type 1 and 2 clinical trials.
It's bonkers that we don't already do this, but apparently this is not current practice.
All right, if there are no more questions from the audience, let's thank both of the speakers. And thank you.